Welcome, everybody, to the MC Toon live show. I'm your host, MC Toon. Today is this is not a debate with a flat earther. This is a conversation with a smart guy, Darryl E. Barry Jr. This will be recorded to go on a podcast at a future date. So the way it'll work is, well, first let's introduce Darryl. How you doing, Darryl?
Doing good. How you doing? Thanks for having me.
I'm great. Glad you're here. Darryl had reached out to me as I had kind of put out an invitation for some things like this, and he said, "How about we do this?" I'm like, "That's great." So the format will be this little intro here. Then I'll go into the kind of the presentation portion, and then after that, if there's any questions from the audience, you can send them out. Now you'll hear me like close up the podcast portion of it. Don't be confused. I'll continue after that, but I'm just signing off on the podcast portion for the future recording. So get your questions ready. Write them down. So, um, is there an echo? People are saying no echo for me. Okay, so no echo for other people. It's just you, Ionian Guardian. So, all right, and all right, here we go. Welcome to the Toon Show. I am your host, MC Toon, and we've got today the smart guy, Darryl E. Barry Jr. How are you doing, Darryl?
Doing great. Awesome.
So Darryl had said that he wanted to talk a little bit about dark matter and dark energy. So he has some stuff ready to go, some presentation. But why don't you first start by just giving a little bit of background on what you're doing right now?
I'm a college student. I have two associate degrees. Currently, I'm working on my undergraduate. I'm at my first senior year. I'm gonna have two senior years. I'm getting a degree in physics and a degree in astronomy. And I plan on going to grad school, eventually being a professor, maybe a little bit of research along the way. And so I have a great interest in astronomy and physics in general. So I enjoy talking about it.
Awesome. Well, I've been excited to hear about this. Dark matter, dark energy is an interesting topic, of course, and it's on the frontiers of our understanding of the universe. So um, hopefully this is enlightening for everybody. So go right ahead with what you've got.
Awesome. And is the sharing okay?
Give me a second. Yeah, that looks good.
Awesome. So I'll be talking about dark matter and dark energy. I'll talk about detection methods, results, as well as a little bit of outlook. And I'll reiterate, I'm not an expert, so I'll be sharing other people's research. But I think the benefit is that it'll be understandable. So this will be actually the third time I've given this talk, and people have responded that they were able to understand the concepts well and that it was interesting. At the end, we'll have some questions or challenges. I know normally a lot of flat earthers talk on this channel, so whether you want to ask a question, I'll answer it as best I can, and any challenges, I'll be happy to crush any flat earth nonsense and keep it going. So dark matter. So basically, this will be the direction of the talk. I'll talk about dark matter, dark energy. I'll talk about the people, prominent people in the past and in the present, a little bit of the findings and theories that's going on now. I'll summarize both topics, and that'll be the end of the talk. So to start with dark matter, it is basically the abundance of missing or invisible matter in the universe. We know it's there because it has very, very observable gravitational effects. I looked into several sources, and there's not a consensus on an exact amount, but it's roughly 80 to 85% of the matter in the universe is dark, uh, pursuant to the amount of gravitational effects that it has. One of the main effects is astrophysicists have been aware for a while that the stability of galaxies was a conundrum given the amount of visible matter we can see, and dark matter accounts for that. So, but still, we're trying to figure out exactly what it is. So it's still considered one of the most fundamental problems in physics, um, but it is still a lively research topic. One of the things I did was I wanted to find out how far in the past the idea goes. And this is the earliest person I found, a guy named Frederick Bessel from the 1800s. He was actually the first I can find who presented the idea of dark matter. It wasn't dark matter in the sense that we think about it. Basically, what he was doing was he was observing perturbations in stars, like the Sirius star Procyon. I thought it'd be interesting to see what they might look like. So if you look at this image, the right is an actual picture of the sky. The left is illustration so you can see the placement. So at the bottom on the left of the image is Sirius. On the right, the brightest star in the bottom left corner. On the upper left corner is Procyon. And basically what Frederick was doing was he was noticing that those stars were not, it was not just staying still, it was wobbling basically. So he surmised there must be something there that we can't see. There was. Basically, he was looking at a white dwarf. He just couldn't tell at the time. But still, that was the first sort of mention I can find of something, some kind of matter that we couldn't see. When we start to get to dark matter proper, the first one to propose it was this guy named Jacobus Kepiton. He was actually a pioneer for photographic astronomy uh, in the early 1900s, a Dutch. He's the first one who proposed dark matter as we can see it, as we talk about it today, I meant to say. And the first one that I can find who measured it was Lundmark. He actually did galactic measurements of a very rudimentary kind compared to what we can do today. But he observed galaxies and noticed their rotations and concluded that there must be more matter there than we can see. As far as current people, these are the people we'll go into more detail about. These are the folks today who basically bring to the fore dark matter as we think about it now, which is Fritz Zwicky, Jan Ort, Vera Rubin and her partner, and Douglas Close. So I'll go into a bit more detail about each of these characters and what they brought to the table in this order from left to right. So Fritz Zwicky, he actually popularized the term dark matter in the 1930s. Basically, he did some observations and found that there was more matter than we can find. A quote from him was, should this turn out to be true, that there was more matter than we can see, surprising result will follow that dark matter is present in a much higher density than radiating matter, or matter that we can see. One of the connecting threads that I found as I went through this research was that technology played a big part. So at the time, the telescope that we're seeing right now, that's an 18-inch telescope at Mount Baltimore. It was new at the time as Wiki. Of course, it's smaller than a lot of the telescopes we have today. But he used that telescope to make observations of the Coma galaxy cluster to find out that the velocity curves he was seeing was too much than what we can find. And he also noticed that, at least he surmised that our calculation methods was probably inaccurate. So he devised three ways that we can utilize to try to determine if dark matter was there. So I'll go into each of those, but the last one is the main one that had an impact on dark matter as we understand it today. So the first one I'll talk about is called the virial theorem. So if you look at this image, this is actually an image directly from his paper. So basically what he did was, if you look at the equation at the top, see if I could zoom in on it. That's actually a very complicated way of writing Newton's equations, F equals ma, force equals mass times acceleration. But what he did was he took that simple equation and applied the virial theorem to it, which I'll talk about. So if you look at the equation, R is the radius from the center of the galaxy, m sigma is the mass of a specific galaxy within the cluster. And basically he applied that theorem in such a way to take into account the mass of everything at a certain radius going towards into the center of the galaxy. And the idea of the virial theorem, even though it's complicated calculating it, me and the graduate student was looking at that paper and trying to work it out, and we still didn't get to the end. But the foundation of what he applied is very simple. So this guy here, Clausius, he actually came up with the virial theorem. And the basic idea behind the virial theorem is basically that the average kinetic energy of a system equals to half its potential energy. So what I'll do is I'll demonstrate a quick calculation to show how that works from some basic principles. So let me stop sharing my Zoom here, and I'll go to my pad momentarily and give you a bit of a understanding of how this works. As you look at MC, is it visible?
Yep.
Okay, awesome. So talking about the Vero theorem, basically the idea is that we have three major forces at play in this calculation. So we have potential energy, or gravitational potential energy, which is going to be the gravitational constant, the mass of a large object and the smaller mass rotating around it, and the radius or the distance between them. You have the force of gravity, which is going to be the gravitational constant, big M, little m, and r squared, because the force falls off at a proportional to the radius squared. And then you have the centrifugal force, which I'll call Fc, and that's basically the big mass, the velocity squared divided by the radius between them. So basically what we're looking at is we have a big mass in the center, that's big M, and you have a small mass that's orbiting around it. And these are the forces that are in play. The kinetic energy as the object is moving. The gravitational force would be pulling the object towards the larger force, and the centrifugal force will be pushing that object outward. And the idea is that in order for the object to not just fly off into space or to not get pulled into the center object and just crash into it, the gravitational force, G m over r squared, has to equal the centrifugal force. So the idea is that those have to equal in order for the system to be in place. And we discussed that there's kinetic energy. So kinetic energy is 1/2 the mass times the velocity squared. So that's a basic sort of kinematic equation. If I multiply both sides by 2, I get 2 kinetic energy equals mv squared, which happens to be the same term at the top of here. So then I can rewrite this and say Gmm over r squared equals, so this time I'll input what mv squared is, 2ke over r. And I can go ahead and do some calculations. So I have radius here, I have radius there, and I can divide both sides by 2 to cancel that. So what I end up with is kinetic energy equals 1/2 Gmm over r. And as we discussed, that was the potential energy. So 1/2 potential energy equals kinetic energy. And that's basically what the Vero theorem says. The Vero theorem basically just takes this simple relationship, and what Zwicky did was he applied this relationship to the universe at large in regards to galaxies. So that's where that comes from. Again, that the specific calculation is a whole lot more complicated, but that's the basic idea. And is my screen back to looking
Yep.
normal?
Looks
MC?
good.
Awesome. So he looked at the Coma cluster, which is this cluster of galaxies here, and he reasoned basically that if you take the total mass of the cluster divided by the number of galaxies, that'll yield the average mass. And basically, putting all these things together, he realized or calculated or found that the amount of mass that must be there for that for the velocities he was seeing was simply more than we can visibly see. The second method he utilized is simply statistical mechanics. He basically counted the probabilities of the amount of galactic clusters in the universe and simply calculated that there were too many for us to account for by simply chance and the visible matter we can see. So not as fun, but he did come up with it. So I wanted to mention it. But the main one he came up with is gravitational lensing. So this is a raw image. The next image that I have will show a sort of uh, uh, some notations that show what's going on. But if you look at this image, these are galaxies. So this is a very deep field image. Even though these may look like stars, each one is a galaxy. And I'll draw your attention to the central part of the image, where if you look at the central part, you can see that things are not necessarily circular. So galaxies are normally circular, but if you look at this, you can see that there are some areas where there's a sort of uh, slash, they call it shearing going on. So what's happening is this is called gravitational lensing, whereby if you have a large amount of mass, it perturbs or bends space. Space-time itself bends, and light goes in a straight direction. It doesn't accelerate or decelerate. So if we look at light and we see that it's bending, that must mean that the space that it's going through is bending. And if you have a large enough amount of mass, what will happen is that that warping of space can actually bend light enough that we see duplicates of objects. So if you look at the central part where it says a lens quasar, that's actually the same quasar. So what's going on is there's a
Oh,
quasar to the back of this foreground mass, and gravitational lensing is bending light in such a way that we're seeing the same quasar twice. And then you know it's the same quasar because they can study the light, the spectra from each quasar, and they match perfectly. So either we have the same type of quasar perfectly being duplicated in different parts of the universe, like quadruplets, or what we found is there's one quasar behind that foreground matter that's being duplicated. And if you look at the lens galaxies on the side, that's called shearing or weak gravitational lensing. So when it duplicates, that's called strong gravitational lensing. The shearing is called weak gravitational lensing, where you can see the galaxy is sort of stretched. So we're seeing more of them, but it's actually stretched at the same time. So it's really a combination, and that's going on because of gravitational lensing. So Zwicky was the first one to hypothesize or theorize that gravitational lensing could be utilized to determine if there's more matter there than we can see by how much lensing is going on. And I want to show a few other examples of gravitational lensing since it's a presentation. This is what's called an Einstein ring. So what's going on is there's a large amount of mass in the foreground, and the matter in the background is actually being lensed around that foreground matter, and it's forming a ring that we can see. But basically, we're seeing the same galaxy lensed around that central object. So that's called an Einstein ring because, of course, Einstein's formula is you know heavy in lensing and relativity and all that stuff. This is called Able 2218 galaxy cluster. And as you can see, there's a lot of lensing going on. There's strong and weak lensing going on. So this one is not uh, uh, marked, so it's kind of hard to see where the strong lensing is going on. But you can see like a galaxy here looks very similar. And you can see the shearing as far as little streaks that's going on. So he's the one who surmised that this can be utilized. And as an example of an equation that we now use to test this, I'm not going to try to work this one out or solve for this one, but you can see that this is the angle of deflection of light that's being lensed. This G is the gravitational constant. This M will be all the mass in a line in a radius from the lensing to the center of the galaxy. C is the speed of light squared, and the R is the radius. So you can, for instance, use this equation to look at and measure the amount of lensing that's going on, solve for M, and you can see how much mass is causing that lensing. You can compare the amount of mass we see to the amount of lensing, the mass we have in lensing, and that'll tell you how much dark matter is there. So that's the idea of gravitational lensing and how it's applied. So moving on to the next person in the lineup, Jan Ort, and we'll speak a few times about his idea of approaching dark matter. Basically, he looked at galaxies and he looked at the rotational curve of the galaxy. So we can look at galaxies, see that they're spinning, and basically he looked at the velocity of the spin and realized that galaxies are spinning too fast to account for the amount of matter we see, and also the galactic clusters are moving around too fast to account for the amount of matter we see. Based upon his calculations, they accounted for about 30 to 50% of matter that we can't see. As we know now, the amount is towards the high end, but basically that's his contribution. So if we look at some of the galaxies he was looking at, he focused a lot of his observations on the Virgo cluster of galaxies. So this printout is basically a diagram of all the, at least a majority of the galaxies in the Virgo cluster. He found that there was at least 25 more mass than we needed than what we can see to allow the Virgo cluster to exist. And I thought it'd be interesting to see some of the individual galaxies. So these are basically zoom ins of some of the galaxies in the Virgo clusters. We can see they all have different names. And this is what he was observing. He was basically looking at the rotations of the galaxies around that's going on in this cluster and seeing that the velocity was simply too much to be accounted for with the amount of matter that we can visibly see. He also looked at the Andromeda galaxy. Andromeda galaxy actually has a nebula partner, just like we have several partners in the Milky Way galaxy. And what he observed was that the approach velocities of the two were about 102 kilometers per second. And that approach velocity was simply too much to be explained by the amount of mass that was between the two galaxies, between the galaxy and its partner. So he's a big contributor. At this time, it is important to mention that still uh, people are on the fence a lot, whether it's dark matter. People had several different ideas. People were thinking maybe there were a lot of white dwarfs out there, or uh, uh, other things that we might not be able to see that were just heavier normal matter. One of the things that came about to get a more accurate interpretation is the work of Vera Rubin. So basically, and I mentioned earlier about how technology was a very big part of how these things improved. Her partner, Kent Ford, actually invented a technology, a new type of spectrometer that had a more accurate receptor in it, the chemical that actually absorbed the light. And what she did was she absorbed the movement of gas clouds around different galaxies, and she was able to utilize this new spectrometer to get a more accurate reading of the spectra and utilize their redshift to calculate that there was more mass than we can see. So to give a visual representation of how that works, here is a visual illustration. So if we look at this GIF, you see the person spinning, and on the left, you can see the person's arms are coming towards us. On the right, the person's arms are going away. So an astrophysicist would say that on the left side of this image, there's a blue shift, and on the right side, there's a red shift. So what happens is with light is something similar to what happens with sound. So like if you're ever sitting in your car on the side of the road and or standing on the side of the road and the ambulance went by, for instance, you notice that when the ambulance is coming in, the sounds high pitched. When it's right beside you, it sounds normal, and as it's leaving away, it sounds lower pitched. Well, the same thing happens with light, except the speed of the overall light doesn't change, but the wavelength is stretched out and the hue changes. So on the left, we would see that a galaxy, for instance, will have a bluer hue. The light seems sort of higher in you could say visual pitch. And on the right side, it has a lower hue. So if you look at the equation at the top, you can get the redshift by measuring the wavelength. And for instance, we grow hydrogen in a lamp, which I had to do in my lab like a few weeks ago, and we take a spectrometer and measure the light. And what happens is you'll see that it emits at certain frequencies. And but you measure that wavelength, you compare it to its rest wavelength, you can get a redshift, and you can multiply that redshift times c, the speed of light, and you'll get the velocity that particle or whatever it is moving away from you. So basically, you can look at the matter on the left side of a galaxy, look at the matter on the right, look at the matter in the middle, take comparative redshifts and calculate how fast that galaxy is spinning. And the idea is that the more mass that's there, the faster it can rotate. And what we found was that there was a lot more mass than can account for given that rotation. So the technology she utilized, this is an example of the telescope she used, at the Kitt Peak National Observatory with force spectrometer. And basically the spectrometer fit on the end of the telescope, recorded the data, and it was the most accurate amount of data that we had to time. Another thing it did was it reduced the exposure time. So the exposure time went from days or weeks or whatever it was before that to about 3 hours of exposure time. So it means every 3 hours, you can capture enough data to make calculations on another cloud of matter moving around a distant galaxy. And they did a lot of studies on them, of different types of galaxies. So these are the equations she utilized. I pulled this directly from Vera's paper. And if you look at this, I can actually just mark on the screen how it works. So basically on the left, this is the gravitational force and the centrifugal force, the same equation that we utilized earlier, except instead of solving it for virial theorem, she solved it for velocity or mass. So basically, if you see there's a radius on the right, radius on the left, that cancels out. There's a small mass at the top on the left, a small mass on the right. And as you can see, that automatically gives us the velocity equation, v squared equals gm over r. And you can solve by simply moving the g from the top on the left, moving it at the bottom on the right, taking the r from the bottom on the left and moving it to the top on the right. And then you have the equation on the right side. So basically, you can study a galaxy, see how fast the gas cloud is moving around it. That'll give you the velocity, and you can solve for mass, or you can think how much mass should be there, and see and calculate the velocity which should be there, and see if the velocity matches. So to give you an example of how the data lined up, so I could explain this graph, and I'll explain it in two ways. A simple way to look at it is simply that if you look at the line at the top, this is the velocity curve that we uh, observe. So this example is a galaxy that they call NGC 6503. At the bottom, it's the radius from the center of the galaxy. So 0 is the galactic core. This is the edge of the galaxy at about 22 kiloparsecs. So basically, once you get from outside the range of the core of the galaxy, if you observe matter at any part throughout the galaxy, it's going about the same pace. Yet, if we look at things like planets in the solar system, like Pluto, is about 100 times farther from the sun than Mercury, and Pluto goes around the sun about 1/10 that, so about the square of the radius. That's what we see based upon the amount of matter with no dark matter taken into account. This is what we actually see with galaxies is this linear curve. And you can sort of think of this curve here that says disk as what the curve would be if there was no dark matter. Basically, if the matter distribution in the galaxy was similar to what we see in the solar system, where there was no additional matter, the farther away you get from the galaxy, the slower things will move. But that's not what we see. The more precise way to look at this graph is, what this graph does is it takes all the components, the matter components of a galaxy that contribute to the velocity curve we see at the top. So basically, if you look at all the gas in the galaxy, it'll contribute to this much of a velocity curve. If you look at the actual galactic disk, like the stars and things in the galaxy, it contributes to this galactic curve, and it requires this much dark matter, which they now call the dark matter halo that's surrounding it and interpenetrating the galaxy. It takes this much dark matter to contribute to the mass of a galaxy to cause the amount of velocity curve we see from the actual matter we see in the galaxy. So this is the type of data we were able to get with the type of measurements that Vera Rubin got, that lets us know that there have to be a lot more matter there than we can see. So the last point on dark matter before I wrap up the dark matter topic, this is like the Hail Mary of dark matter topic as far as I'm concerned, which is Douglas Cloak. So what he realized was, which was the same thing I thought when I started looking to the topic, well, how do you know something else is not going on? How do you know that the calculations for of Newton's equations with this stuff, because the formula we had earlier was based upon Newton's equations. How do we know that stuff works at these far distances and heavy amounts of matter? So what Douglas Cloak realized was, what we need to do is find a situation where the dark matter is displaced from the majority of visible matter that we see. So what we're seeing here is something that's called the bullet cluster. So it's the collision of two clusters of galaxies. And when I say collision, we're talking about clusters of galaxies. So it occurs over millions of years. But over millions of years, these two different clusters of galaxies combine to make a very large galaxy cluster. And this is a image of the visible matter that we see, like if you were to, point a regular telescope at it. Now, this is an image taken with the Chandra X-ray telescope. And what we found was that if you see this pink area, that's actually plasma that's within, or I should say between the two galactic clusters. So basically, these areas here are the concentrations of galaxies that sort of just basically move past each other because there's so much space. But the plasma that's floating around in the galaxies was sort of stripped from the galaxies a bit and still hung up out in the middle. And this area of matter is several times more than the matter in the actual stars and components of the galaxy. So this area of mass is about 7 times more, or up to 7 times more than the matter that we have on the side. And if you look at this next image, the blue is a coloring in of where the focus of dark matter would be, or where the focus of dark matter actually is after they did gravitational lensing. So to show a composite image, again, the middle is the plasma, which is up to 7 times more massive than the bulk of galaxies, which is on the left side. But they found that the gravitational lensing is here. So this slide actually shows a the contours of gravitational lensing. So earlier we looked at some images where you can actually see the streaks in the image. These would be where those shearing streaks and things like that would be. And the center of these, you could say the center of the bullseye is where the focus of gravitational lensing is occurring when we study the images and calculate look at the gravitational lensing. So what's going on is the majority of visible matter is still here where the plasma is, but the gravitational lensing is focusing on the galaxies in the cluster, which means that the galaxies must have more mass than we can visibly see, even so much mass that it outweighs the plasma, which means that there must be dark matter there accounting for the gravitational lensing that's going on, that has the gravitational lensing focusing on the galactic clusters rather than on the plasma that's floating in the middle. So the actual paper, as you can see at the bottom, is called a direct empirical proof of the evidence of dark matter. And I pulled this image here directly from their paper. And this came in the early 2000s. And, I would consider it like the definitive evidence that dark matter is there. So as far as the findings that we have, we still, it's still one of the fundamental problems of physics. We still don't know exactly what it is. All we know is that it's not baryonic matter, which means that, regular matter that we can see it had electrons, protons, neutrons. The electrons interact with light. We can see it. Whatever it is, it has gravitational effects, but it doesn't interact with light in the same way. But we know we have to have a dark matter halo because, galaxies are not flying apart. So dark matter has to be integral to the formation and stability of galaxies. I looked at a few of the experiments that they're working on. One of them is they're trying to crash things together to see if they can spot a missing amount of energy or momentum. And two of the ideas they have for dark matter, one of them is called WIMPs, WIMPs. That stands for weakly interacting massive particle, and FIMPs, freeze in massive particles. My understanding is these particles are basically the same, except WIMPs would have formed in the early universe and self-annihilated when they came in contact with their own type of particle. And eventually an equilibrium was reached, and that would be dark matter. The freeze in, the difference would be that they would have kept being created and until the universe got too cool for them to be created. That's why it's called freeze in. The lady who wrote this, or this not her wrote this paper. This is actually from a talk. She actually came and gave a talk in UT Austin about a month ago. And what they're going to do is do some deep probes of the early universe to try to see. She's going to try to determine, get more information to see if it's WIMPs, if it's FIMPs, by studying the early universe, where we can try to surmise how the universe was at that period of time and see what the creation of dark matter would have been like. So that's the dark matter topic, about halfway through. And now I'll start talking about dark energy. So dark energy, basically what I did was I took the data from the previous slide, because just like with dark matter, you look at different sources, the percent they give it varies. But if I was to base it on the sort of general proportions for the previous slide, is about 68% dark matter. I think dark energy. I think the highest I saw was like 70 or 72, so it's not much different. So basically, the matter energy density of the universe, dark energy, outstrips both dark matter and regular matter. And the idea is that dark energy is basically a term that's given to what's causing the expansion of the universe to accelerate. So we know that the universe is accelerating. I'll talk a bit about how, but we know the expansion is now getting faster and faster. And we don't really know that it's some kind of energy, but the term that they give it, whatever it is causing that accelerating expansion, they call it dark energy. Um, I'll talk about one. There's several different measures that they utilize to study dark energy. I'll talk about one because each of them is like a talk in itself. What I'll do is talk more about the steps that came about for them to find out that the expansion is accelerating, so you can understand what those steps were. So I'll start with the past figures. This lady is Henrietta Leavitt, and what she did was uh, the short story of how they found out was using standard candles, basically looking at objects in the universe whose luminosity we know and calculating how far they're moving away from us and seeing that the rate is changing is based upon the work of this lady who basically studied a certain type of star called a Cepheid variable star. So there's several types of variable stars. And basically what happens is, stars like our sun is a main sequence star, is in the middle of its lifetime, is fusing a lot of hydrogen and the helium. What happens is when that fuse starts to run out and the star starts to cool, it shrinks. Basically, the pressure from its fusion is helping keep its equilibrium. And as it shrinks, the space gets smaller, it heats up, and then it expands again. When it expands, it cools, and it keeps pulsing by that dynamic. And so basically, the star is starting to die as it's peeling off the main sequence. What she found a certain type of star where its pulsation rate is directly linked to its luminosity. She studied thousands of stars. She cataloged these stars, cataloged their luminosity, and she learned that if you find one of these stars that's pulsing at a certain rate, you can plot that rate, and now we have a formula to look at a star that's pulsing at a certain rate and see its luminosity, and that's what's called a standard candle. So basically, we know its luminosity already, and we could use this simple equation to get its distance. So just like similar to, I should say, gravity, luminosity or radiance falls off at a square distance portion. It's like how you up close to a light is bright, the farther away you get from it, it dims. Is a very consistent dimming. So if you know the luminosity of an object, you can measure its brightness and you can apply this formula to get its distance. The significance of this is Hubble actually utilized this or applied this to determine that the universe is accelerating. So he utilized cepheids, studied those things at different distances, and what he found that when he plotted the rate of velocity going away from us at different distances using that same simple formula, he found that they had a linear distribution where the farther we went away from us, the faster things were moving away. I believe that's why it's called the Hubble constant, because if you measure it at any given time, it seems constant. But of course, we'll get into how it's changing. But this is directly from his paper that he wrote in 1929, where he realized that the farther away you look, the faster things are moving away from us. It's a linear distribution to the point that you can get the distance of something, uh, apply it to the Hubble's constant by dividing the velocity, then you'll get the distance that is moving away from us. So it's pretty cool. So what we're going to talk about next is these three fellows. They applied what we talked about earlier, and basically what they wanted to do was they wanted to get sort of a constant of deceleration. So the idea that they thought at the time, according to Perlmutter, they thought the universe is going to be shrinking. So they wanted to get a parameter that eventually the universe is going to slow down, going to shrink because of gravity. They wanted to get a sort of deceleration parameter. And that's why they started studying different galaxies. But the thing is, Cepheid variables we can only see so far. So we'll take a look at how they utilize the concept to expand upon it and find another way to look even farther into the universe than Cepheids can look. Two background concepts we want to consider as we're talking about dark energy is the cosmological constant. It started with Einstein, with that he thought that the universe was constant. He inserted this lambda value into his equations to stop the universe from expanding, contracting, basically, to balance out gravity. Of course, now we know that is expanding and is accelerating. So he realized that that idea was wrong. We will come back to that because now that we know that the acceleration is expanding, people think that that constant is basically almost equivalent to what dark energy is. Another thing we want to keep in mind, we talked about redshift with the Doppler effect. Since since galaxies are being moved away from us as space expands, there's a concept called cosmological redshift. So basically what happens is when galaxies move away from us, not because they're spinning, but the entire galaxy moves away from us, the entire galaxy redshifts. And we could utilize the same equation to figure out the redshift of the galaxy itself. So they call that cosmological redshift because galaxies are only moving away. So to give you an idea of how this works, if you look at the top image, that's basically uh, the emissions that we capture from a galaxy. And like I said, we can put, for instance, hydrogen in a lab. In the lab that we did a few months ago, we had hydrogen, we had nitrogen, and a few other things. And you look at them, and they all emit specific light at specific ranges. So when you look at a galaxy and you look at the distribution of the light, you can see, okay, that distribution is hydrogen, but it's moved to the side a bit. That'll be the redshift of that light. And we can compare it to the base uh, wavelength, get the redshift of it. And it gets a bit more complicated when the galaxy has fallen away. So the equation on the left is the one that we will use that I got from my astrophysics professor. The redshift over 1 plus redshift times the speed of light, and then you get the velocity that that galaxy is moving away from you. So these are some concepts to keep in mind because as we go back to Cepheid variables and then extend that farther with farther distance, standard candles, these concepts will be in place. So what we want to do now is apply these concepts of cosmological redshift, uh, the constant, and what scientists basically did was the way we were able to do this to get more accurate measurements is updating the accuracy of our chain. So if you look at this image here, it basically shows the process that was utilized to make more accurate distance measurements starting from radar, getting a more accurate distance for the astronomical unit, going to parallax, then Cepheid variables again more accurately, and then you using those to calibrate what we call type Ia supernovas or white dwarf supernovas. So I'll go through each of these steps, and then the final step of actually seeing that it's expanding is actually quite simple. So starting with radar, what they did basically was shine radar off nearby objects like Venus, and we know how far Venus is from the sun in astronomical units by using this simple equation here that's called Kepler's third law, where the period of a planet, the time of its orbit, directly relates to its distance from the sun. So basically, we know Venus's distance in astronomical units. We use radar to find its specific distance from the sun, and then we apply that distance to astronomical units, and now we have the exact distance of an astronomical unit. If you're curious, Venus is about 0.772 astronomical units from the sun. Uh, we apply that its actual distance of about 108 gigameters, and then we get about 150 gigameters for an astronomical unit. So now we have a very accurate distance of our distance to the sun, and we can use that to extend more accurate measurements. So the next step is called parallax, where basically we have our accurate distance from the sun in AU, and we look at the wobble in a star, where it's basically apparently wobbling back and forth as we are on one side of the sun compared to the other side. That angle we can call the parallax angle, and we can use simple circular trigonometry via the equation at the top left, and we can get our distance from us to that star. The significance is we can do this on a Cepheid variable star, and now we have a very, very accurate measurement of our distance from a Cepheid variable star, which makes it a more accurate standard candle. So if you look at this graph on the right, this is an actual measurement or calibration of Cepheid variable stars with the Spitzer Space Telescope using Cepheids in the Milky Way and Cepheids in our neighboring stellar body, the Large Magellanic Cloud. And as you can see, if you look at the curve, it's very, very precise. So basically, if you look at a Cepheid variable star that's taken, let's say 10 days to post, you go up to the line and go to the left, you can see its magnitude is about 13. And this has been consistent over thousands and thousands of stars, which makes that a very significant standard candle. But these things can only be seen so far. So about, you can see in the image there, about 10 to the 6 light years. But what we can do is, now since we have a very accurate distance measurement to Cepheids, we can find a Cepheid variable. Like here's one in the Andromeda galaxy. This is actually the first one Hubble discovered. And if you look at the left, you can see that it's a bit dim. If you look at the right, it's a bit brighter. And what we can do is find a Cepheid variable in the same galaxy with a white dwarf. And when the white dwarf goes supernova, now we can get a very accurate distance measurement to a white dwarf and use that to extend our distance measurements further. So if you look at this image, this is actually, and this is not a type A supernova, just put that up there because we're talking about it. This is another image of Sirius. So we looked at the actual star earlier in the earlier slide. Now Sirius is the bright star on the left. Sirius B is what's called the white dwarf. So when the star about the size of the sun dies, it extrudes its outer layers as a planetary nebula, and it leaves behind its core, which is about the mass of the sun, but is only about the size of the planet Earth. If you look at the right, you'll see that the white dwarf is brighter. It emits very brightly in the ultraviolet and the X-ray. And what happens is these things can only get so big. So the idea is that the mass of these things is so heavy and such a small volume is putting a lot of pressure on the electrons that's orbiting, that's moving around the mass. And what's called electron degeneracy pressure is what's keeping the thing from collapsing. But the more pressure is put on the electrons, the faster they have to go to counteract that pressure. And since they can't go faster than the speed of light, that sets a limit on how big they can get. That limit is about 1.4 solar masses. It's called, I believe, the Sandreskar limit. So once the mass reaches that limit, let's say a white dwarf is absorbing matter from its companion star, where two white dwarfs collide and merge. Once it reaches that 1.4 limit, the pressure ignites usually they're made of carbon, it ignites the whole core and the whole thing explodes. And what they did was they looked at enough of these things to find that their distribution of their light curve is very similar because they all explode around the same amount of mass. They have to get the same 1.4 solar masses. They have about the same amount of mass. They're made of about the same amount of stuff. Usually it's carbon, but the lighter ones might be more helium. But the differences are not that great. So if you look at the top, that's a literal plotting of different light curves of different type Ia supernovas. The bottom, they made the corrections for the slight differences. You can see they match up. So if you look at a type A supernova, you observe the spectra, you see where it falls on the spectrum at the top. You make corrections for it, and now you have a very solid standard candle that you can utilize to measure distances. Now, if you look at the images here, you can see how bright they are. So the top shows a normal galaxy sitting there. Perlmutter actually devised a way to calculate, to predict when one is going to explode. That's the only way he can get to access big telescopes like Hubble and things like that, because the time is so valuable. But he calculated a way to find out when they were going to explode. When he finally published his paper that won him the Nobel Prize, he used about 42 supernovas. So still, they happen very rarely, like about 1 in 100 years for any particular galaxy. But if you look at the bottom, you can see how bright they are, right? They're about as bright as the galaxy, which means that as far as you can see a galaxy, you can see a type Ia supernova. We know the luminosity very accurately from comparing them, the distances that we got from Cepheids. We know how distant they are. We can measure their brightness. We can use the formula we looked at earlier to calculate its luminosity. Now we have a solid standard candle, and we could apply these things to, for instance, Hubble's law. You can compare what we're seeing now as far as the distances, how fast they're moving away, to what Hubble measured. and we found out that the speed at which they're moving away from us is getting faster, and that's how we know the expansion is happening. So that whole the acceleration is happening. So that whole sequence of events is what contributed to us finally being able to put these different equations together and seeing that yes, acceleration is happening, but not only is it happening, but it is accelerating, and that's how these things came about. So to get another look at the entire chain of events that put those things together. So as we start to wrap up the dark energy topic, this is an actual plot of the curve of different supernovas at different distances. So, and this is actual data. So if you look at the bottom here, this supernova was at about -8, in the past, billion years in the past. These at the front were, this is now very nearby. So these are probably in nearby galaxies here to us. And this is a distribution of the velocity curves that were plotted. The curves, the little lines that we see are actually models of different types of universes. So basically the red curve shows a universe that's collapsing. So basically what we can do is we can, of course, look at the universe now. We can see what the expansion rate is right now. We can see what the distances are to things, what the size of the universe is now. So all the graphs have to match what's going on now because we can see now. But then we can calculate, okay, if the universe is collapsing from based upon where we're at now, what the universe look like. We know that's wrong because the universe would have, it's too young a universe. The critical universe means a universe where the matter distribution is such that the universe is expanding, but is expanding slowly. So, it started with a more rapid velocity curve at the start, then it levels out, and it never quite, contracts, but is just very slowly expanding. The coasting universe is one where it's basically a consistent expansion rate. This would be consistent with what Hubble graph looked like, that very linear graph curve. Of course, his data was only so accurate. When we look at the more accurate data we can get today, the plot of data matches the accelerating curve, which shows that at the Big Bang, the acceleration was, of course, a lot steeper. It started to slow down a bit because of gravitational distraction. At a certain point, the expansion caused the distribution of galaxies to get to the point where the gravitational pull lessened, so that dark energy started to dominate. And then we can see that the acceleration curve is starting to increase. And the supernova data matches that, which is how Perlmutter was able to show that uh, the expansion rate is accelerating. I say Perlmutter because that's the one who I focused on the most, but it was actually two different teams. It was Perlmutter's team. There was also two other people who won the Nobel Prize, Smith and Rice. So two separate teams independently observed supernova data. They both came to the same conclusions. They both presented their data around the same time, and around, I believe it was around 1998. And by the end of the year, people accepted that acceleration was happening because these two independent teams did that. And what the Nobel Prize people did was they got leaders from both of the teams, and they gave them all the Nobel Prize in 2011. But there's actually two independent teams that came to the same conclusions. So to wrap up dark energy, basically cosmic acceleration is expanding. We don't know exactly what it is. We talked about it a bit in my astrophysics class. I think it might actually be quantum fluctuations, basically, some kind of quantum activity that's going on within space itself. That seems it'll lend to the fact that the density of dark energy seems to be constant, even though the density of matter decreases as the volume of the universe increases. The density of dark energy seems to be consistent, which is seems to contribute to the acceleration, I would say, because its density is staying constant. And then we go back to the lambda uh, uh, term I mentioned earlier. Basically, they're sort of referring to dark energy as lambda now. It's still inconclusive whether the volume of dark energy was different in the past, depending on what model you look at, what Hubble's constant you look at. The data is a bit inconclusive, but people are trying to get more detailed measurements of the universe to get a better picture of whether the rate of expansion, how much it changed in the past, and similar to how we compare Hubble's graph to the last graph I showed, where you can see the difference in the curve and the slope of the curve. the idea is that if we get more accurate data, we'll be able to get a better accuracy of how the curve changed, if it, at all. So to look at a bit of that data as I wrap up, two different projects happen, going on now at least. One is at the Mayo telescope in Arizona. It's called the DESI project. The telescope is the one on the right. And what we're looking at now is the focal plane of that telescope. So basically, if you look at the right, that's about 5,000 different fiber optic cables that's coming out. Each of them are robotically controlled, and each one can be pointed at an individual galaxy. So what they're doing is they're making the 3D picture of the universe, and this thing is accurate enough and it has enough data collection points that it can, take thousands of data collection points per night, and they're going to make a 3D picture of the universe to get a very accurate image of the universe so they can study it. They're going to apply one of those other methods I talked about, but I didn't really study it in detail, called the baryonic acoustic method. It's basically there's sort of a wave, you can say, going through the universe as a result of the Big Bang. And galaxies actually form at certain distances based upon that. It's quite interesting, but I didn't look into it in detail. But they're going to compare the actual data with the model and see if it's changing. And they actually released their first amount of data this year. This is actually from the data released. This is only 1% of the data. This is 1% of the three-dimensional picture of the universe. It's going to be a 5-year program. And when it ends in about 2 or 3 years or so, they'll have a very accurate 3D picture of the universe to make that study and get a better idea of what's going on with the accelerated expansion.
This has a look of a laser show. I like it.
Yes, it does. And I can actually show you an actual video. This is like a GIF, but the video actually zooms in a bit. So I can actually show you after the presentation. But it does actually look like that. That's the first thing I thought about as well, like a concert. Another project is at my hometown, UT Austin. So this is the UT Austin Observatory, the McDonald Observatory. And their telescope is slightly different. This is the focal plane of their telescope. They call it the VIRUS virus. And if you look at the data on the right, I'll zoom in for you. It's sophisticated enough to where it can observe a galaxy, and it could actually tell you the distance the thing is moving away from you. It can tell you the type of spectra it is. So it can tell you the type of object it is. It could even tell you the speed it's moving away from you. So it's pretty sophisticated, but it is going to make a sort of 3D image of the universe, but it's slightly different than the DESI one. But they will be able to get a very accurate picture of the universe, and they'll use that data to try to determine how the acceleration of the universe has changed or not. So pretty interesting stuff. So this is a zoom in of some of the things they're looking at. This was actually from their data as well. Some of the things that they're finding out. So there's a white dwarf, galactic nuclei, and so forth. So pretty cool. So that's still ongoing as well. Like I said, this stuff is really new. But they're using the same thing. They have 32,000 optical fibers in theirs. It's controlled by 100 instruments instead of 5,000. But they can still move around, point at specific points in space, and get some accurate data. So to summarize everything as we wrap up at the top of the hour, topic of dark matter has a long history, as I showed, even though at first they were sort of mistaken about what they were looking at, but they did mention things that we may not be able to see. Gravitational lensing played a big part, but there's other things they're using as well, rotational curves of galaxies. But we know dark matter is there. We can see the effects. Dark energy, one of the main ones is type Ia supernova, but there was a lot of other things as well, baryonic acoustic oscillations, other stuff. I read it about a little bit, but I didn't look at it in detail. But I mean, at least 10 things they're looking at that they utilize separately to individually or independently confirm that the acceleration is expanding. And we know that they're inherent parts of the universe. So if you ever look at a scientific paper or something and they say lambda cold dark matter, that's what it's talking about. The lambda refers to the dark energy, which whatever it is something that's causing the acceleration of the universe, the expansion to accelerate. It seems to have the same qualities that Einstein was putting into his equations, even though he put it there for the wrong reasons. But the qualities of it seem to be the same. And dark matter, they call it cold because, of course, when we heat something up, we heat water up, it starts to boil and it flies away. But dark matter is pretty consistent in its position, so we call it cold because it's staying together like cold matter that's not boiling away and flying apart. So thank y'all for listening. I hope you enjoyed it. I know it was a lot of information. So now we'll end the podcast and go to question and answer. And I'm open to any questions or challenges, wherever they may be. And I have some time, so however long if Tune wants to go, I will make it happen.
All right. Well, Darryl, thank you very much. And if you are watching the Toon Show podcast, um, you can or listening to it, you can find it if you want to watch the actual presentation as well. You can find it online on YouTube. Just search for Toon Show. And thank you very much. All right, so now question and answer. I've got a handful of I've got some super chats in general and some questions I've collected while you were talking. Um, and
So let me stop the screen share here. Let's see what we got.
There we go. All right, so I will. I've collected them. I will hopefully do a good job. Just a second. I got to pull up my notes. There we go. First question: Does dark matter need a container?
Is that a serious question? No, I don't think.
It's
I wouldn't
from
be surprised if I had to ask that.
it's from when Dave Weiss, or Dearth as he is affectionately called, debated Professor Dave, and in that debate, Dearth claimed that spectroscopy needs a container.
Oh my God.
Yeah,
No,
he
it doesn't
really
need a
said that.
container. It's just matter, just in case they're really curious.
All right. MK Ultra says Merry Christmas and Happy Hanukkah, and I responded
Awesome.
to MK Ultra with Nesgadol Hayasham in the chat. Mark Beiser says tonight we are the dumbs. Yeah, you're the smart guy, and the rest of us are the dumbs. We are learning from you. Some good information. Let's see. We've got Icy Spin says so we can put away the tomatoes. No need to throw tomatoes at Darryl. Let's see. All right. Icy Spin says, what are your thoughts on tired light? Or light extinction, as some flat earthers say.
I looked into that a bit. My professor talked about it a bit. My understanding is simply that things get in the way of the light coming from different parts of the universe, so it like interferes with it. So I don't. I mean, it seems like a pretty simple thing. I mean, they call it a weird name. I mean, I can see the kind of confusion from the name light extinction, but I mean, it's similar to like if you take like you remember they had those little guns that shoot a bunch of like ping pong balls or something. Like if you just shoot a whole bunch of that, but you put something in the front of it, some of the ping pong balls are going to be bounced away.
Yeah.
So, the more stuff that's there, the less ping pong balls that hit you. So that's all it is. So the more stuff is there, the less ping pong balls hit you. And if you have enough stuff there, then it's just, very little ping pong balls. You can't get a good image of it. And that's all it is. That's all that is.
I think, flat earthers claim that Zwicky was measuring tired light, and that's why it was doing what it was doing. It wasn't apparently, light just gets tired and then goes slower because it's tired. All right.
It's a
Let's see.
confusion a bit. I mean, it does stretch and, so I mean, you can kind of say it gets tired because the longer wavelength light has less energy. So, with redshift, it does stretch. So I guess you could say that, but I'm sure flat earthers mean it in a very distorted way like they
Well,
often
yeah,
do.
they're all. I mean, to them, there's nothing more than a couple thousand miles away ever. So
Mm.
I don't know how it can get that tired in such a short amount of time. You'd think if when you were looking just at the stars immediately above the horizon, they're farther away than the sun would have to be because they're somehow embedded in the
Right.
dome on the other side of where the sun is. That when you look at them, when you're far away, then they would be more tired than when you're somewhere else looking at the same stars. But I don't think there's any place on Earth where you find a drastically different shift in the wavelength
Of course, it
based
is
on your
run from that. I
location.
mean, yeah, because whenever they say distances what causes the horizon, well, you can see the stars way back there. So what's going on? I guess we shouldn't see any stars less than a certain height or something, right? I mean, something.
I don't know. They're farther, yeah. Okay. The Cretan Bull says this guy is smart and knows what he's talking about. Worst flurf ever.
Thank you. That is a big compliment. The worst slurf ever. Yeah.
Icy Spin says, does Earth's gravity affect V vision, right? Of far away and
I mean, I
things.
guess
And then, oh,
technically,
and there's a little more. He says, my super chat, he says, my supper chat is basically that there are distant things that Earth's gravity may cause lensing before it reaches our eyes. So, our Earth's gravity.
question. We talked about in class how there's something called gravitational redshift, like light leaving from a gravitational source, it'll shift. So it seems reasonable to me that light coming towards a gravitational source might blue shift. But the thing to think about that is the mass of the planet Earth is so small on a galactic scale that whatever change would be very small anyway. So, whatever change, I'm pretty sure if you did some tight calculations, it's there. But I mean, it's not going to
Yeah,
make a big
it's
difference.
how many significant digits can you measure? It's
Exactly. Right. So,
Yeah, like when they were calculating the amount of light displacement around the sun versus light displacement around Jupiter for the 1919 eclipse,
gravitational
Eddington, all
lensing.
that, the amount of shift of starlight around Jupiter was way too small to measure at the time, and maybe still I don't remember the exact amount, but it's a very small amount of shift. So they're like, well, that's not enough. We can't measure that, but we can measure the shift in the vicinity of the sun because it's large enough in mass.
There you go. And Earth, of course, will have less than Jupiter. So there you go.
Yeah, yeah. So, all right, got another one there to put in the the list. Let's see. Professor Parks, PhD, says, and he's an astronomy professor. He says, feeling poorly, so I have to watch tomorrow, but wanted to send some love. So maybe he'll give you
Thank
a
you.
grade on this.
That would be great.
I'll give him your email address so he can send you any information he might have.
Please do. Help me
He's
get where I'm going.
I'm on his Discord server, and of course, a lot of his students are on there, and so I was talking with a few of them on there about how fortunate they are to have such a great professor. So, Mr. E-Man gifted 10 memberships. Thank you for that. And then Icy Spin says, isn't Tired Light part of the new universe age talk? Yeah, so like I think it's a way to salvage young Earth versus old Earth
Oh, really?
creation,
Hmm.
maybe. But I think for the most part, young Earth creationists don't disagree with light shift. They just attribute it a different cause. Like it was placed there like that, I think.
That I don't know about.
So, all right, let's see. We've got Raichi says, could it be that the masses are wrong, or there is just some sort of yet undetected slash unidentified energy? And this was during the dark matter portion. She asked that.
I suppose so, but I mean, you'd have to look at closed data and somehow explain how the gravitational lensing is different from the majority of the mass. Fact is, like I've heard you mention several times, MC, there's always a degree of error in measurements. Just like how when you go, like we talked about Zwicky, his calculations were off because his data wasn't as accurate. His measurements were off. His process was good, but his amount of measurements of mass were a bit off, right? Just like how Vera has more accurate calculations than her previous. So the fact is, as time goes on, our measurement of the amount of mass will improve, but I don't see how that would change the fact that the majority of the mass is here when the majority of the mass we can see is there. So it seems to me at this point, it'll be a matter of a more accurate calculation of how much dark matter is there, but not whether dark matter is there. Unless you can somehow disprove flow, there's matter there we can't see. You know,
I've heard other proposals, and I think for the most part, they're just people that are just kind of, whiteboarding ideas. So, for example, another would be, is maybe the formula for the law of gravitation wrong, where instead of the formula over r squared,
Hmm.
right? Maybe it's not squared. Maybe the exponent is a variable, and based on the distance, as something's farther away,
I
maybe
got you.
gravitational pull is actually not squared. It's maybe only over 1.9 or 1.8. So it's the amount of gravitational attraction is larger when it's farther away.
I
But
think that's
yeah,
possible.
I don't think I think that when the analysis is done and stuff like that, it ends pretty quickly.
I think a constraint on that. I think the possibility would be constrained by the fact that like the Andromeda Galaxy is very close to us, right? So and then we have distance galaxies. It seems like uh, we whatever is affecting Andromeda, if it's a distance thing, would not be affected as much. At least it would not be affected as much as distance galaxies. But we can look at Andromeda and see other galaxies that have similar masses. So I think that will put a constraint on that.
Yeah, yeah,
We would have to see an Andromeda type galaxy, but see, wow, the mass is very off. But I never seen any indication that the masses of galaxies that we calculate far away or at any distance is very different from nearby galaxies, even though we can see that they're the same type of galaxies, have the same type of sizes, the same types
yeah,
of stars in the inside. So that would be a constraint on it. Maybe somebody can find it's R 2.1 or something, but it'll be limited. You know what I'm
yeah.
saying?
It is nice that there are so many galaxies to look at and compare. Um, so here's a question. This is from me. So you had mentioned early on that when you look at a galaxy and it's rotating, one side of the galaxy is redshifted and the other side of the galaxy is blue shifted. But as the galaxy moves away from us, the entire galaxy is redshifted also, so it's compounded, right? So you've got the blue shifted side of the galaxy is also redshifted because of expansion,
That's correct.
right? But when you look at, I don't know why I'm kind of answering my, well, maybe I'll let you answer. We've still got this redshift blue shift that's happening in the galaxies there. Can you explain on how you
That's right.
separate those out?
Certainly. So what happens is we can look at the whole of the galaxy, like the image that I showed earlier. We can look at the whole of the galaxy and see the shift. So now you have the shift of the whole galaxy. And then when you look at the right side of the galaxy, it's shifted in addition to that. So let's say the rest wavelength, and these numbers are going to be a bit off, but let's say the rest wavelength of hydrogen is 4,000 angstroms. And the whole galaxy is at 9,000 angstroms, but the right is at 905 and the left is at 8,995.
Mm,
You see what I'm saying?
yeah,
So then now what we're working is we're not counting hydrogen's rest uh, uh, wavelength as the rest wavelength. We're counting the center of the galaxy as the rest wavelength. So now we're saying what's the redshift between the center at 9,000 and the right at 9,005? And that velocity will give us the relative velocity between the center and the edge, and that is the rotational velocity. You see?
okay,
So that's
yeah.
how that's done. That's a very good question.
So the numbers you gave, I know were just contrived, but is
That's
that
right.
kind of a reasonable scale where the amount of redshift of the entire galaxy is large and the
Yes.
relational left to right side of it is rather small,
Yes. For my
right?
first homework in astrophysics, we had to calculate that. And that was the
Okay.
redshift on either side. It was 5 angstroms.
All right. There you go.
And my numbers are about off, but they're actually pretty close. Like hydrogen was about 4,000 something. The whole galaxy was about 9,000 something
Hmm.
angstroms of redshift, a longer wavelength, and the right and the left was each five plus five minus. So that's pretty accurate to what they really see.
Okay. Um, and then to go to further on that, Webb telescope is looking at things that are farther away, that are older, that are significantly more redshifted. So all of the wavelengths, to my understanding, all of the wavelengths of a Webb telescope is below visible light. Is right?
Well, I don't know about that. But I
Okay.
know that if something is below visible light, we can't see it. But I haven't looked into that, so I can't really say
Okay.
about that.
How far infrared it
I know they
is?
do a
Okay.
lot of different frequencies, but yeah, I don't know about that.
Yeah, I know there's a collection, a large collection of different sensors with frequencies. So okay. Well,
But
so
yeah,
somebody
but
else.
it'll work the same way. I can
Yeah.
tell you that much. Like any frequency of light will still be redshifted. So if you're looking at ultraviolet light, for instance, it'll still have a redshift, and or X-ray. You can look at X-ray and it should.
Yeah,
But I don't know how they do it, but it will still have a shift.
that's
Just
true.
like all
Yeah.
the
So
electromagnetic radiation.
so the things
So
that are formerly unseeable with our eyes would be redshifted into visible spectrum potentially, right?
Exactly. And redshift it would be infrared or something. We'd have to just look at it at a different frequency. But
Right.
I haven't looked at into that in detail. But my understanding would tell me that's how it would work. And astronomers have come to UT that's specifically what they focus on. Like some of them, they focus on infrared, and some focus on gamma. So they all have their uh uh
Their
you know
their
things that they like, and
specializations.
that's what they
Yeah.
do. Yeah, exactly. So
Okay. Another question from Rachie says, "So what's the dark energy exactly?" That's the question, is it? And what is dark matter exactly? As a black body is meant to be theoretical.
well, I mean, it's like this. The CMB is pretty close to a perfect black body. So that's one example of one that's pretty close. To me, WIMPs seem to be a good choice, but some people say that's not a good choice. So I don't know. I can't really say. My professor was saying the quantum fluctuations for dark energy seems to be a big thing, but I didn't really understand it, so I don't think I'll go into detail about it. I can simply say it's still unknown. They don't really
Okay.
know. All we can say is we know dark matter is there because we can see the gravitational effects. Like the previous person said, maybe we were a bit off on the amount of matter, but we can certainly say that there's more matter there than we can visibly see. And as we saw on the acceleration curves, we don't know what it is, but we know the expansion is accelerating. So all we can say is that is there, but we don't know exactly what it is. We can say it's not baryonic, it's not interacting with light the same way as far as dark matter. Um, and it seems like the density of dark energy seems to be constant since the acceleration is expanding as the density of matter decreases as the universe expands. But other than that, we can't really say anything for certain. So, but maybe that's something you could join in the research and help figure it out.
Yeah. Okay, I've got two questions. I'll put them together back to back here because they kind of have a similar topic. GIEG 81 Geig 81 says, just joined, so missed the presentation, but can dark energy be caused by a white hole?
It's interesting. I've actually never heard mention of that, so I don't know. One thing I can say that tells me that gives me doubts about that is the expansion is very uniform. The acceleration is uniform. So in order for it to be white holes, the white holes would have to be very uniformly distributed. And if there's anything like black holes are usually centered around, laws of, like in the center of galaxies and things like that. So what I know at my lowly undergraduate perspective, it seems unlikely, but I don't know. It could be. I've never heard mention of that. It seems like they would have to be very uniformly distributed to account for what seems to be a general uniform acceleration. Other than that, I don't know what other constraints would be.
Okay, and then Icy Spin asks, have we ever discovered a white hole?
I don't know. I never actually heard mention of a white hole before. Yeah, I never seen that
Yeah,
anywhere.
I think it's strictly hypothetical at this point.
Gotcha. I mean,
So
I think I've heard people say that the other side of a black hole might be like spewing matter somewhere, but I think that was based upon the idea that black holes were sucking stuff up. So
yeah,
I think we know that's not the case now.
it's a
So
vacuum there, and then it pokes through
yeah,
to somewhere else. Yeah, I
exactly.
think that was more fantasy than an actual proposal, but it could be wrong. Somebody might have actually thought that was a thing. So, all right,
Ironically, though, now they're saying Hawking radiation happens. So at least they theorize that it happened. So in that case, black holes are not like just sucking stuff up.
yeah,
So
something gets out,
mhm.
somehow, so energy gets out. Yeah, again, hypothetical. So, all right. Well, if there's any other questions, I think I've covered all the ones I saw, but let's see. So clarification on the one from GIEG 81 says, I mean, uh, is the whole galaxy a white hole? Doesn't that explain dark energy?
Okay. Well, I mean, that seems like just a different way of saying dark energy permeates the universe. So that seems more nomenclature to me. If it acts the same way, calling it a white hole universe or a universe permeated with dark energy, that seems like pretty much saying the same thing. We still don't know exactly what it is.
All right, another one from Jeebus says, maybe a bit more serious. Is there any idea why the dark matter hangs around in the galaxy clusters and remained there despite the plasma cloud in between being more massive?
Very good point. My understanding is that the dark matter is already around the galaxy. So basically, you have these two galaxy clusters that are coming together. Plasma is just floating around in between them. So I guess the idea to think about would be, uh, uh, even though I guess it's kind of reversed. Like if you think about two glasses of ice water, right? And when you throw them together, the water will probably go past each other more than the ice. The ice is sort of clinging together a bit,
Mm.
right? So think of the plasma as the ice that's like clinking together, and the galaxies are sort of kind of like just flying by more easily. So that's kind of like what happens. So galaxies already have dark matter around them, plasma just floating in the middle, and when the two galaxies start to run past each other, the plasma just sort of just sticks together because it's more free flowing. I guess I think of it something like surface tension of water, like how water you put two drops together, they sort of form one drop, something like that. So the plasma sort of does that, like they kind of form one drop in the middle, two smaller drops, and the galaxies sort of just keep on zooming by. And then the gravity of each sort of slows them down, and they form a cluster on either side of the plasma that sort of up as one drop in the middle. So that's my understanding of it.
Um, okay. I had a
Does that
response
make
on
sense
that,
how
but
I
oh
explain it?
yeah, oh my response in that was it kind of seems that and maybe this is a thing already, but that the dark matter, whatever it is, right, was already there, and that's why the galactic clusters formed around it.
That's right. That's what they're
Yeah,
saying. Oh, that's she was going back to that. Yes, our understanding is that dark matter is what necessary for galactic formation because they would have simply flung apart. Like the velocity was too much for them to stay together without dark matter to even form. So, yeah,
yeah,
dark
it
matter was
would.
always there. It
Yeah,
seems to be.
it because without some reason to coalesce, why would the universe not be homogeneous and just everything
Right.
be evenly distributed? Why is there a clump of matter?
Right.
So yeah,
So the idea, and that's why they refer to WIMPs and FIMPs as forming in the early universe. They formed along with, you know, uh, uh, electrons and protons, and just the
yeah.
electrons and protons became neutrons, and hydrogen and helium started coming out, and the dark matter was already there and just clumped around them, and then things started clumping up more and more because of the slight quantum perturbations, and galaxies started forming, and now you have galaxies with dark matter already there, gas floating around them, and then these galaxies form clusters, gas floating all in the middle of them. Then the clusters collapse, and the plasma gets sort of stuck together in the middle as one puddle. And now you have the galaxies on either side, and then you have the bullet cluster. So it's kind of like a brief history of the of the formation of the bullet cluster.
All right, Icy Spin has a very profound question. Have we ever discovered a flat cosmological body on the back of a space turtle?
Not yet, but I'll hold out hope.
I'm sure that's the real purpose of the Webb telescope. Uh, all right, well, that is it for the questions. Um, Darryl, it's been great. I learned a lot here. I think it's a good topic. I look forward to your further education, and maybe you can come back when you've got a couple more years under and are a professor.
Yes, sir. I appreciate that. It was
That'd
a
be
pleasure to
cool.
meet you as well. So I'm a big fan of your channel and your video. So
Well,
awesome.
thanks. If you're unfamiliar with Darryl, he did debate on Modern Day Debate. I mentioned this I think before, but the link to that to one, were you on more than once?
I was only on once. It was a few
Just
years ago.
okay, is in the description already. He spoke with Wotan. Um,
It was an interesting debate. You also check it out.
it's a good one. Wotan was he couldn't play his normal games. It was great. Um,
Face palm protection, as FTF says.
yes.
Have it with you.
Brenda says that Jaren's really upset at me for the space turtle video. Um, yeah, Jaren sent me a message overnight. It was middle of the night for me. He was very displeased with that video. Um, he's Is it possible to strawman a model that doesn't exist?
Right?
So I have been accused of strawmanning flat Earth, the flat Earth model. But I ask, well, then what is the model? And I'm never on the receiving end of a model to not strawman. So how can you strawman a model that doesn't exist? What if there's no model? Whatever you want it to be is not a strawman. You can just
Right.
invent
They have to do it that
whatever
way.
you want. Yeah,
That's right. Because it got debunked so hard, they had to stop saying stuff because they knew it was going to get debunked again. So
yeah.
now it's like some ephemeral. The sun is electromagnetic, and everybody has their own perspective. And oh my
Their own
gosh,
dome, yeah, or whatever.
yeah.
Yeah, yeah. But yeah, and of course the sarcasm is sometimes missed. I'm being sarcastic with the space turtle. But to be honest, it's not any different than any more right or wrong than the actual model that they don't provide. So
And of course, the fact is we base it off what they say. Like I talk with several flat earthers, and I give them the video, and of course, what they say is that's not a real flat earther. They don't really know. And that's how I ended up talking to the guys I was telling you about. They would say that's not a real flat earther. Talk to that guy. Then I would talk to that guy, and then they say talk to somebody else, and then they say talk to somebody else, and then you know what I mean. So it just all it's.
it's all, yeah. Then when you finally do get somebody that's like, here's our model, and it's just some vague thing.
Mhm.
Here's a picture. It's a picture, a picture of some
Yeah,
magnetic
like a
field.
meme.
That's not a model. What
Mhm.
predictions can you make with it? What plausible mechanism does that have included in it? Nothing. Um, let's see. GEIG81 has one super chat, says, at Rachy, does Darryl have a YouTube channel?
Yes, I do actually. Actually, I have a lot of flat Earth videos there. I visible them because I just got fed up with it after a while because it never changed. But I may put them back so y'all can see it. But maybe MC Tuna, I'll send it to you if you want to put the link in the
Yeah, I'll do that.
next to the yeah. So I'll send it to MC Tuna and he'll put the link to my YouTube in the
The
description.
description, yeah. Awesome. All right, well, Darryl, it's been great having you. Anything you want to say as we to close out?
Just thanks for having me here. It was my pleasure, and I will let you know when I have some information so I could come back.
All right, sounds good. Don't hang up. I want to talk to you afterwards. Everybody else, we'll see you next time.